This is the third video on Chapter 24, Linear Transformations. And here we're going to take an example, and the function itself is very simple, but we're going to do some sort of complex things with it. So our two vector spaces that we're looking at are both R3. So we're considering V is R3, but we're going to take the standard unit basis for V. W is R3, but the basis we're going to use is these three vectors. And in the notes I labeled those X, Y, and Z. And we want to find our linear transformation from V to W is just the identity function. So T of X is equal to X. So at first it all seems very simple. We're just going from R3 to R3, and our function is the identity function. Now we want to find the matrix for T and use it to express this vector as a linear combination of X, Y, and Z. Now when we say find the matrix for T, we mean in the sense of note 301, not theorem 299. So in other words, we're not looking for the matrix A such that multiplying on the left by A will give us this linear transformation, because that would just be the identity matrix. So we want to find the matrix for the linear transformation. Now, it's easier to work with T inverse. T inverse is the function from W to V, and T inverse of X is equal to X. That's because, T of X is just X, and so the inverse function of that is also just X right here. So T is its own inverse, basically. Okay, so now we want to find the matrix for T inverse. That's easier than finding the matrix for T. So let's let A be the matrix for T. That's what we want ultimately, but in order to get there, we're going to find the matrix for T inverse first. So A is the matrix for T, A inverse is this matrix. Where did that come from? Well, you'll notice that the columns are just the vectors X, Y, Z that we have right here. So X, Y, Z, we just took the matrix A and we formed A by making these vectors the columns of A right here, or A inverse. Now, why did that work? Why is this the matrix for T inverse? Well, if you look at T inverse going from W to V, remember, this X, Y, Z right here, these are the basis elements for W. Now, the function value of X is 1, 1, 1, and these are the coefficients you use to express 1, 1, 1 in terms of I, J, and K. The basis from V. The function value of Y is 1, 0, 1, and these are the coefficients you use to express 1, 0, 1 in terms of I, J, and K. Likewise, Z is the vector 2, 1, 3, and these are the coefficients you use to express the vector 2, 1, 3 in terms of I, J, and K. So that's why A inverse is this matrix. That means, that's a typo, that means that A is A inverse inverse, so A is this matrix. I calculated that ahead of time. So if we take our matrix A, remember we're interested in expressing the vector -4, 2, 1 in terms of our basis X, Y, and Z. So we multiply on the left by our matrix here, and we get the vector -3, -11, 5. So now take our basis X, Y, Z, -3 times X minus 11Y plus 5Z. and we have expressed -4, 2, 1 as a linear combination of x, y, z.